the deep networks perform very well for many data sets and is scalable to large data sets. So why do we still need kernels? Well, I think kernels, we have several advantages. The first advantage is that kernel is easy to use. There are only a few parameters to tune. For deep network, you have a lot of parameters to tune. It's not easy to make it work. And also, kernels perform very well for small data sets. So let's look into the details. So this is the content of today's tutorial. First, I will review some basic materials of supported vector machines. Basically, I will put everything into a mathematical framework, which is different from the lecture. Use the kernel trick, which how to combine kernels with supported vector machines. Then we get the kernel SVM. Then we continue to talk about kernel selection. I think this is very important in using kernels. Without picking the right kernel, you cannot have good results. The next two are two advanced topics. I will not go into detail in this two, but I will just show you some high-level idea how multiple kernel learning works, how scalable kernel methods works. Okay, let's begin with support. Look at this very simple example. We have blue points, we have red points. We want to classify these two sets. And there are many lines here. Either of them can classify these two sets well. I think you probably learned perception before. Using perception algorithm, it will lead to any line here. It can possibly lead to any line here. This is one, perception is one algorithm. So for supported vector machines, we are seeking a maximum classifier. We want this decision boundary, this very thick black line that appear in the middle. We want that this decision boundary to be far away from the two sets. We want to find such a line. So this is the max margin classifier. This is supported vector machines. So let's see how we put it into a mathematical framework and how we get this line. Okay. So I'll put all the dots here. So we want to find this line that separates these two sets well. Assume that this line, we can denote this line with equal to 0. So in the two-dimensional case, you have, say, this is x1. This is x2, then this line can be denoted as x1 minus x2 equal to 0, right? Which is basically y equal to x. So the line that closest to this, to the circle, we denote it as w times x plus b equal to 1. So why we set this equal to 1? Essentially, it may not be equal to 1. It can be anything. It can be equal to a, but we can normalize it. We can normalize with the weight, with the norm of this a, and we get a 1 here. So this doesn't matter. And the line here is wx plus b equal to minus 1. We want to maximize the distance between these two lines. So how can we get this distance? Oh, sorry. Suppose there are 2 points here. This is x plus. This is x minus. So this is a vector, right? How how can we get the distance between the vertical distance between this? So we do some vector calculation. So suppose that the vector we can denote it as x plus, and the vector here we denote it as x minus. Then we do a projection. Because the slope of this line is w, then we do a projection of this vector along this direction. Then we times w. Then we get the distance. Oh, it's not distance. We have to renormalize it with the length of this vector. Because this dot appears in this line, so we have wx plus equal or plus b equal to -1. Note that we have a minus here. So then we subtract these two terms and we get which is equal to 2, right? So for this term, we have this is equal to 2 divided by the length of this vector, this weight. So this is the distance of these two lines. So we want to maximize this distance, which is why we call it max-margin classifier. Subject to the constraint that all these dots appears here, all these dots appears in this region. So we can put this into an optimization problem, which becomes like this. Because we maximize this, which is equal to minimize the weight of W, subject to the constraint that all these circles appears in this region and all these plus appears in this region. So this is why we have the optimization formulation here. This is a very easy to solve optimization problem. We can fit it into some optimization software, we can get solution. But before that, we need to study some problems of this optimization problem. So here requires some optimization knowledge, but I will briefly introduce the idea here. So basically, to study this optimization problem, we study the Lagrangian function. This is how we introduce the Lagrangian function. Which is equal to the original objective minus, here we introduce a slack variable, which is called alpha I. For every constraint, we introduce a slack variable, and we times them together. So we want to study this function. Here are some very nice things here. So this function has 3 parameters, including the parameters of the original optimization problem, which is W and B. And it also includes some additional parameter. This parameter, we introduce it by ourselves. For each constraint, we introduce this additional parameter. And here's how the amazing thing happens. Suppose that we first maximize this alpha, then we minimize over W and B. And this will lead to the original optimization problem. Let's see how it works. First, we look at the first part. We maximize this function over the additional parameter alpha, right? And here we have an additional constraint. I forgot to put it here, which is non-negative. And look at this function. And we ignore the W and B. We only care about the alpha. We want to maximize this function with respect to the alpha. And we find that if yi times if this is greater than equal to 0, then the value becomes if any of the constraints violates this requirement, then it becomes infinity. If any of the requirement is not satisfied, then the value is infinity. So we want to minimize this function over. Of course, this part is actually ignored, right? Because this value is infinity. We want to minimize over the parameters. For any reasonable value of w and b, we get a non-infinite value. So we directly ignore this part. So this becomes the original optimization problem, right? Oh, sorry. Let me quick. Greater than or equal to 0. Can you see it? Which means that if the constraint is satisfied, then we have a non-infinite value. If any of the constraint is not satisfied, we have infinite value. This is maximize alpha. Maximize this function over only this select variable alpha. And we have additional here. And this is equal to this, right? Then we minimize over w and b. Because we have infinity here, we just ignore this part. And then we got the primal optimization problem, which oh sorry. Let me check. Which is exactly this optimization problem. Can you say it louder?
When you maximize alpha, to do that, you have to take the derivative with respect to alpha.
Right. The derivative is this, right?
Yeah.
If this is greater than or equal to 0, then we can set alpha to 0.
Yes.
If this is negative, then we can pick alpha to infinity. So this value becomes infinity. Because this is a linear function here, right? We only care about the sign of this parameter. This can be unbounded. If this sign is positive, then we can set this to be set this to 0. We get the maximum value. If this is negative, then we set this to be positive infinity. Then we get a positive infinity here. Because this is a linear function, you don't need to care about the exact value. You only need to care about the sign of this term. Okay. So using this formulation, we get the original optimization problem. But if we switch the order of these two optimizations, we get another problem. We just switch the order of the optimization, we get another problem. So what's the relation between these two? Definitely we have this greater than or equal to this. Because for any value, this is greater than or equal to, for any function value, this is greater than or equal to this. Sorry for this. Okay, then how do we get solution of this optimization problem? The optimization problem which we switch the order. We first minimize over W and B, then we maximize over alpha. Oh, okay. We want to get a solution of this. And this is the lower bound of the original optimization problem. Then we take the derivative, right? We set it to 0, just as he just said. We take the derivative of this. Let me erase this. Okay, well, let me erase this. So we want to minimize W and B over W and B. So we take the derivative with respect to W and B. So for the original function, for the first term, we have this is a derivative, right? For the second term, this is a derivative with respect to W. We set it equal to 0. The derivative with respect to B is set it equal to 0. So for this equation, we get W is equal to alpha yi times xi for this. Then we plug this into the original equation, and then we maximize over alpha. So let me put this. Then we maximize this over alpha, subject to the constraint. The new constraint is here. Then we got this new optimization problem. Sorry?
So first we maximize, in the first step we maximize alpha, and then with respect to alpha, and then minimize with respect to W and B, right? And now we are doing...
Right, yeah, in the reverse order.
Yeah, so why are we doing that? Or just to say it's same, or like why are we...
Yeah, so in the first order, we get the primal problem. In the second order, we get the dual problem. And there's some correlation between these two problems that we want to explore. And by studying the relationship of these two problems, we get some properties that I will show later. And sometimes the primal problem is hard to solve, and the dual problem is easy to solve, and we can solve the dual problem instead.
Is there a reason why that is the primal and it's the dual, or it's like interchangeable? Like, you can call this primal and that dual, or that...
Yeah, either way is okay. Either way is fine. Yeah. But since I introduced this first, so I call it primal, then I use the Lagrange function, I call this the dual. So this is another optimization problem, which is different from the primal optimization. I call this dual optimization problem. As I said, the original primal optimization problem is this. This is a primal. This is a dual. We want to minimize, and we want to maximize here. If this Lagrangian function is convex, then these two coincide that are together, which means the two problems are equivalent. We can either minimize the original primal problem, either we maximize the dual problem if the Lagrangian function is convex. And there are some nice properties here. The first is that the weight is a linear combination of the points, right? Alpha times yi times xi is a linear combination of these points. And we also have a KKT condition. Actually, I have derived the KKT condition before, right? In the primal problem, right? If the constraint is satisfied, then we have alpha I equal to 0. If the constraint is not satisfied, then I can make a value. So this is the constraint here. Since that alpha W is the linear combination of the original points, note that alpha I is non-negative if the constraint, if this is equal to 1, which means that only the points on these two virtual lines, they will count in the weight. This dot, they will not be counted in the weight. Only the dots along the virtual line, they will be counted in the weight. So this is why we call it support vector. So as I have just said, only the points on the boundary that matters. We can remove all the points, not on the boundary, and we can do the same optimization. We can get the same result. Okay, this is the hard margin classifier, which means that the original two sets can be classified, can be linearly separated. But this is a special case. We have a blue point here. The original set cannot be classified linearly. So the original framework only applies when this blue point disappears. But if we have this blue point, how can we use the original framework to handle this special case? So here we introduce a slack variable. We allow that the constraint is to some extent violated. So we introduce another variable, and we put a cost in the optimization problem, which we pay a cost for not classifying it accurately, and we get the software margin classifier. And we can repeat the original process, and we can get similar properties, which means that if the points they are correctly classified, then the weight is 0. If they are on the boundary, then the weight combination is between 0 and C. If they are not correctly classified, then the weight is C. This is the intuition we get by exploring the dual problem, by exploring the combination of the primal problem and the dual problem, and we get some insights here. And this is why we want to do that before. Okay, so okay. Let me draw the plots again. So if they are linearly separated, then we put a decision boundary here. And this is the virtual line, this is the virtual line, right? And we can solve it. But if we have a plus here, the original problem cannot be solved because there is no solution, right? Because we cannot linearly classify the two sets. Then how do we deal with this problem? So if this point, if this plus appears here, the decision boundary may appear here, but these 2 points, may appear here, but these 2 points, they are misclassified. If they appear here, only 1 point is classified. So we must explore a trade-off, where to put this decision boundary, right? So we add a cost. We add a cost to those points that are misclassified. So this is why we have the second term here. We add a cost to these points that are misclassified, and we also introduce a variable c, which how we maintain the balance between the original objective function and the cost of misclassify these points. This is how we introduce c here. How to determine the c here, I will introduce later. It's related to primary selection, and it's quite important. If you set c equal to 0, then I guess the point will be directly ignored. It just appears the original decision boundary. If you put c equal to infinity, then there's no solution again because you cannot linearly classify them. So we have to maintain a balance between how to classify the points and how the misclassified points, the penalty we pay for the misclassified points.
Wait, so if you put c equals 0, you got the original problem,
Right.
right? And in that case, I mean, before when you say, when you distribute, you can only
So if c equal to 0 here, then this problem is different from the original problem because we have slack variable here. We can always set this to be equal to 1, and we got a solution. This solution may not be the original solution, but this still has a solution. Am I clear on that? So the previous presentation doesn't use any kernel in it. We want to combine kernel with the support vector machine. So this is how we call kernel SVM. So before talking about that, I want to talk about kernel trick. Why we want to use kernel? Kernel is a method to map the original feature to high-dimensional feature, so that in case the original feature cannot be classified, but if we do the mapping, we can classify the data set. And here's the example here, and I quite like this example. So for this example, the dots cannot be classified, right, in the two-dimensional case. You cannot put a line so that the red points and the blue points are classified. But if we map it to a three-dimensional case, we can classify them. Let me show you how we do that. So suppose the coordinates are positive 1, and this is negative 1, negative 1. This is for the plus, this is for the circle. We have 1, plus 1, minus 1. So we cannot classify, we cannot put a line here so that the two sets are classified. But we can turn it into a three-dimensional case. This is the second two-dimensional. Suppose this is x1, x2, and we put the x1 times x2 here. So for the plus, we have plus 1, for the circle, we have So the third coordinate, that's quite different. For the plus sign, for the plus data, this is positive. But for the other, this is negative. So we can classify based on the third coordinate, which is x1 times x2. So I put it a three-dimensional figure here. It may not seem quite obvious, but by using the third coordinate, x1 times x2, we can classify the two sets. This is why we need feature mapping, why we need the kernel, why we need to map our original low-dimensional feature to a high-dimensional feature. So note that in the original problem, we have inner product between x1 and xi and xj. We can replace this inner product with the kernel so that we get a kernel SVM. And in the function, we also have an inner product. We can also replace this with a kernel so that we get a kernel version of SVM. So everything keeps the same, but we have a kernel here.
Without this y argument, so why is there a y argument?
I think you can merge these two, merge alpha I with yi. You can get another parameter. That's fine. Either way is okay. So the commonly used kernels are RBF kernels and the polynomial kernels. So for the RBF kernel, basically, this is a Gaussian function. This is x prime. Looks like this. This is a Gaussian function. Basically, this means that if the two points in the Euclidean space, if they are far away, then this kernel value is small. If they're close, then this kernel value is big. So this is the meaning of RBF kernel. So for the polynomial kernel, so this is the inner product of 2 points to the power of d. So we first ignore the d here, the c here, to the power of d. So we have d equal to 2, then this becomes x. Suppose x is in 2 dimensions, right? We can expand this. We can directly write the feature mapping, which is the function phi. We can just expand this because the power is low. And we can see that in the feature, we have x1 squared, x1 times x2, x2 squared. So in the previous example, I attach a term x1 times x2 here, right? So this is basically a polynomial kernel, second order polynomial kernel. In the second order polynomial kernel, we introduce another additional term x1 times x2. I think you need to pick the right decision boundary for different kind of kernels. You can to expand the feature function, so you can see how things work, and then you can decide the decision boundary for different kind of kernels. And there are a lot of parameters to pick here. In the RBF kernel, we have to pick the bandwidth, which is sigma. And also in the original optimization problem, we have to pick the parameter c, right? How we do that? There's no easy way. We use cross-validation. So this is how it works. First, we partition the data into m, and typically we use For each part, we use each set, train the original SVM, and then we get an error on this validation data set. And we average the error over all the parts. Then we pick the C or the width of the kernel with the minimum error. So this is how cross-validation works. So usually we search over the log scale. So this is, suppose we want to pick C, then we search over the log scale, which is, we can set it to be 10 to the power of minus 5 to 5. So this is MATLAB denotation. We search it over 10 to the power of minus 5 to 5. We search over the scale. So for the width, we can set it to be similarly. Search it over the log scale. So this can fasten the process. Otherwise, you have to search from, say, this is quite small, 10 to the minus 5. This is quite big. If you search over the original scale, then you have 2 to the power of 5 models to train. That will do a lot. But here we only have, so that's why we want to search over the log scale. So the previous is the basic content of, now I will kernel. Multiple kernel is still a currently refers to papers. So here's the main idea of multiple kernel learning. So how to pick the kernel itself is a problem. Although we usually use RBF kernel, we use polynomial kernel, but they may not be the best kernel. We usually use them because they work well in many data sets. It doesn't mean they're optimal. There are some unknown kernels may perform better than RBF kernel. So multiple kernel learning gives us a way to explore the optimal kernel combination. We can use a combination of many kernels. We can use a total of k kernels, and we can add a weighted combination of them, subject to constraint that they are greater than or equal to 0, the summation is 1. We have this constraint because we have to keep the original format a kernel, because for kernel we have to have positive self-definite property, right? So this constraint can keep the original function a kernel. And this is just a normalization. Then how do we learn the weight combination? Well, one simple way is to put this framework into the original kernel SVM, and then we optimize better together. But you have to be very careful. You have to put some regularization constraint on beta as well. Otherwise, you will have all kinds of problems. And how to learn this weight combination is also a research problem. And I think for detail, you need to refer to some papers. But here, I want to show you one example. This picture, take this picture paper. Basically, we want to classify blue points and the green points. And this x-axis means the distance between the blue points and the points. For here, they're quite close, right? For here, they're far apart, right? Okay.
Points and
Green points, sorry.
green.
Okay. I want to classify the two sets. And we use a combination of 5 kernels that with different weights, from 0.01 to 100. We use a combination of these 5 kernels to classify these two sets. And you can see the kernel weight here. If the dots they are close to each other, then the kernel with small bandwidth to play a more important role, right? You can see this line, which corresponds to the width of 0.01. But if the two sets are far apart, then the kernel with big bandwidth to play a more important role. Look at this line. This corresponds to the width of 10, right? So this shows how, for different scenarios, we may have different kernel combinations. So next, I will mention a little bit about methods. Recall that optimization. This is the original optimization problem. We have the pairwise term here, which means that if there are n data set, then the term here can be n squared. If n is quite large, then this is uncomputable. If n is 1 million, then n squared is quite hard to compute. So this is a problem with kernel. And also in the prediction function, the summation, the number of terms in this summation is linear with the number of points. If n is quite large, then this prediction function is also hard to evaluate. How do we overcome this problem? So before talking about the technique, I want you to look at the primal problem again. So in the primal problem, there's no such pairwise term, right? In the primal problem. But in the primal problem, we cannot use the kernel because for the RBF kernel, which is in this form, this is the distance between the two data points. This is the kernel, RBF kernel. We only know the kernel function, but we don't know this feature function, this feature mapping function. So we have to use kernel implicitly. So that's why we have the pairwise term there. But if we can calculate this function out, then we can switch to the original primal problem. Then we don't have the scalability issue, which means that the original pairwise term does not appear here, which means that the decision function is this term does not scale with n. It is only scale with the dimension of the features. If the feature is d dimension, then this is of order d. But here we have order n, right? We have the pairwise term. So how do we compute this, given the RBF kernel? Of course, there's no closed form solution. But we can do approximation, right? We can come up with a function phi hat x, phi hat y, which approximate the original RBF kernel. And we want to find such function which can do the approximation. And here's the one way to do this. Called random kitchen. So in random kitchen sinks, it teaches us how to expand this function by taking the Fourier transform. We can take the Fourier transform of this RBF kernel. We can write this function as the integration we can write this RBF function as the integration, the integration is from minus to positive. And this function is also Gaussian, right? We can see this function here is also Gaussian. The original RBF kernel is Gaussian. this spectrum function is also Gaussian. So we can view this as a probability distribution. The integration of this function is equal to 1. So we can sample this function because the original domain is minus infinity to positive infinity. We cannot use finite term to approximate this function. We can just sample it. We can just sample this Gaussian function and compute this feature function. So this PW is the domain of this is from minus infinity to positive infinity. And this is the integral. We can sample this function. So we can use m samples to approximate this RBF function. So for each term, we sample Wi from this distribution. Then we compute this function. After that, we concatenate them together. We can use m samples and we get a vector. And we can use this as a feature function to approximate the original feature function, which is infinite dimension. We can use m samples to approximate the original kernel. This is how random kitchen works. Here's the main insight. The Fourier transform of the RBF kernel is still Gaussian. And we can sample the frequencies of the transform of the spectrum function, and we can approximate the kernel functions. And the accuracy of the approximation depends on how many samples we have. Of course, more features, more accuracy we get. But it also depends on the data. And you can try this out. I want to introduce you to the tool of libsvm. I think it's, you can directly open the link here. And this is a commonly used tool for kernel SVM. You can specify the type of kernel here. I think, right. I think this is options. You can have linear kernel, polynomial kernel, RBF kernel, or any other kernels. I can play around with this software. You can play with the kernel parameter selection, kernel weight selection, parameter selection. You can also examine this random kitchen sinks, which means that you can compute the feature mapping and with a linear and then use this feature mapping with a linear SVM and compare it with the original RBF kernel SVM to see if they are equal to each other. You can verify this. And here are some references that I mentioned. The first two are for multiple kernel learning, and the third one is for random features for large-scale kernel machine. Basically, this is random kitchen sinks. Okay, any questions? If not, then I will be here for questions if you have any. Okay.